Greetings, class. This is Lesson 13, Conditional Probability. Here's what's coming up in the next few lessons. Besides this lesson, we'll talk about independent events, and then how we make a partition of a sample space and derive the law of total probability. We'll then discuss Bayes' theorem to end the module, which concerns updating probabilities in a clever way. The idea in this lesson is to update probabilities as we obtain more information. So, for example, if A is the event that a person weighs at least 150 pounds, then the probability of A certainly depends on the person's height. For instance, if B is the event that the person is at least 6 feet tall versus B being the event that the person is less than 5 feet tall, that certainly affects the probability of A. As a concrete example, let's toss a die. We'll let A be the event that we see a 2, 4, or 6, and B is the event that we get 1, 2, 3, 4, or 5. So unconditionally, all by themselves, the probability of A is a half and P of B is 5/6. Now, suppose we know that B has occurred. Maybe our friend has told us. So there's no way that a 6 can come up. Then the probability that A occurs, given that B occurs, is given by the notation P of A given B equals 2/5, and that equals, not coincidentally, the cardinality of the intersection of A and B divided by the cardinality of B. We'll get into details on that in just a minute. So, the probability that of A depends on the information that you have. The information that B occurs allows us to regard B as a new restricted sample space. And in that case, assuming we have a simple sample space where all the elements have the same probability, then the conditional probability of A given B equals the cardinality of the intersection of A and B divided by the cardinality of B. Let's divide top and bottom by the cardinality of the original sample space. Then, by definition, that equals the probability of A intersect B over the probability of B. Very nice. And now we have the following formal definition. That is, if the probability of B is greater than 0, the conditional probability of A given B is given by the probability of A intersect B over the probability of B. Remarks: if A and B are disjoint, then the probability of A given B equals 0, because if B occurs, there's no way that A can also occur. And you might worry, well, what if the probability of B equals 0? We don't like dividing by 0 after all. I would say, don't worry, because in this case, it actually makes no sense to consider the probability of A given B. As an example, let's toss 2 dice and take the sum. I'm going to let A be the event that we see an odd toss, in other words, a 3, 5, 7, 9, or 11, and B will be the event that we see just a 2 or a 3. This is when we do our sums. So the probability of A equals, since 3, 5, 7, 9, 11 are all disjoint, we add up the corresponding probabilities, and those are 236, 436, ... 236. We had a table of these things previously, and you can figure them out for yourselves. When the smoke clears, that equals a half. So the probability that we see an odd toss is a half. That's interesting. The probability that we see a 2 or a 3 is the probability of 2 plus the probability of 3. These are sums. And those probabilities are 136 plus 236. And that equals a 12th when you add those up. Then the probability of A given B equals, by definition, probability of the intersection over probability of B. The intersection of A and B is just the event that we see a sum of 3, which has probability 236. Probability of B from above is 1/12, and so the ratio 236 and 1/12 is 2/3. Very interesting. So what we saw, the original probability of an odd toss was a half. But once we got the information that we saw either a sum equal to 2 or a sum equal to 3, then that probability of an odd sum went up to 2/3. Very, very interesting. Here's a more complicated example. Let's suppose we have a box of 12 socks. So 4 are white, 8 are red. Let's select 2 of those without replacement. I'll let A be the event that the first sock is white, B is the event that the second sock is white, and C finally is the event that both socks are white. So I guess you can easily write it as the intersection of A and B. So first of all, the probability that we have the event C occur is by definition the probability of A and B. So both the first and second socks are white. By definition of conditional, that's the probability of A times the probability of B given A. And let me switch to English for a second. The probability of A is that the first sock is white, 4 out of 12. The probability of B given A is the probability that the second sock is white, given that the first one was. And since the first one was white, I only have 3 left in the pool for the second one, so that's where I get the 3/11ths from, and that ends up equaling 1/11th. Meanwhile, the probability of B, let's do that next. And I got to say, that's one of these things as you get good in probability, you could intuitively say, well, given that I don't have any information about what happened on the first sock, the probability of B is unconditionally 1/3. That's going to turn out to be the right answer, but let's see if we can do it formally a little more carefully. So the event B is A intersect B or not A intersect B. In English, it's all the stuff in B that's in A plus all the stuff in B that's not in A. Since those two events are disjoint, the probability of B is the sum of those two disjoint probabilities. P of A intersect B plus P of not A, complement of A intersect B. Now we'll apply the definition of conditional to both of those pieces of the sum. And the first one, P of A times P of B given A, we already did. And in the first part, that's 4/12 times 3/11ths. The second part, the probability of A complement, well, that's just the probability that the first sock is red, 8/12ths, and the probability of B given A complement is 4/11ths. The probability that the second sock is white, given that the first sock was red, 4/11ths. When the smoke clears, you get 1/3, which is, bang, intuitively what we thought. And again, as you do more problems in prob and stats, you'll get a better feeling for this. Here's a great example. A couple has 2 kids and at least one is a boy. What's the probability that both are boys? Now, before I go any further, let me just say I did this problem, I don't know, maybe in 10th or 11th grade when I was on the math team, believe it or not, and I got it wrong. I guessed it was 1/2. And let's see why I was wrong. We'll do the problem correctly now. Here's the sample space, all sequences of boys and girls. So girl, 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 boy, boy, girl, boy, boy. Where, for instance, BG means we had a boy first and then a girl. So I'll let C be the event that both are boys, boy, boy, and we'll let D be the event that at least one is a boy. So girl, boy, girl, boy, boy. And here's how we calculate the relevant probability. I want the probability that both are boys, C, given that at least one is a boy. That's event D. So probability of C given D equals the probability of C and D over the probability of D. Now, it turns out in this example, it just happens, look at the sets, that C is a subset of C and D. So the conditional probability then simplifies to, in this example, probability of C over probability of D. The probability of C, unconditional, that you see a boy and then a boy, is 1/4. The probability of D, since it's a simple sample space, is 3/4. So the ratio is 1/4 over 3/4 equals 1/3. Now, like I said, my intuition was wrong. I thought it was 1/2. And the problem was that we didn't know whether the event D meant the first or the second kid. So not quite as much information as you would have thought. Now, if you thought this was an interesting example, as you get more information, you can make some even more surprising findings. So let's look at our next example. It sort of looks the same, but this is an honors example. Now, a couple has 2 kids, and at least one is a boy born on a Tuesday. It sounds a little crazy, but this at least one boy is born on a Tuesday. What's the probability that both are boys, just like before? Well, here, it's a lot more complicated. I got this completely wrong when I first heard the problem. When my friend pointed out I got it wrong, I thought about it for a long time. And you have to define these sort of intermediate events, BX and GX, that you had a boy or girl born on day X, where X equals 1 through 7 days of the week. So, for instance, X equals 3 indicates a Tuesday. And then you can formulate the sample space as these ordered pairs of girls and then boys, or boys and then girls. And here's the notation. S equals all these messy things. For instance, GXGY means that you had a girl born on day X of the week, followed by your second kid being a girl born on day Y. GXBY means the first kid was a girl born on day X, second kid was a boy born on day Y. So you can have 4 combinations of boys and girls and 49 combinations of X's and Y's. So the entire sample space has cardinality 196. Unbelievable. So in the previous example, the sample space cardinality was only 4, and now it's just tremendously bigger. And this is what causes the issues. I'm going to let C be the event that both kids are boys with at least one born on a Tuesday. So that can be notated in the form BXB3, so the second kid is definitely born on a Tuesday, or B3BY, so the first kid was definitely born on a Tuesday. But in both cases of this union, both kids were boys. Now, the cardinality of this set, you might think it's 14, but it's really only 13, because we want to avoid double counting the possibility that both boys were born on Tuesday. We don't want to double count that. Now, the event D is there is at least one boy born on a Tuesday. That's the event C union, the following stuff that incorporates girls. So C is just 2 boys with at least one being born on a Tuesday. And the second part in the union for D is that you could have a girl being one of the kids. So the first part of that second part in the union is GXB3. That means that you had a girl born on day X, boy born on day 3. And the second thing is boy born on day 3, girl born on day Y. So it turns out here there's 27 possible elements in the event D. 13 are coming from C, and 14 are coming from the second half of that union. Okay, so finally, after all this work, the probability of C given D equals the probability of C and D, or the probability of D just like before. Just like before, C is a subset of D, and now C has probability 13 over 196, and D has probability 27 over 196. So the overall probability, the probability that both are boys, given that at least one kid is a boy born on a Tuesday, is 13 over 27. Much closer to a half than in the previous example, where the answer was only 1/3. Wow, what a fantastic example. This is a tough one, though. Finally, let me talk about a couple properties analogous to the axioms of probability. These are properties of conditional probability. First of all conditional probabilities are between 0 and 1. No surprise, they're probabilities. The probability of something happening in the sample space given any event is 1, because something still has to happen. If 2 events are disjoint, then the probability of their conditional union is the sum of the conditional probabilities. So again, not a surprise. And then the same kind of thing holds for infinite disjoint union. Okay, well, this ends the discussion on conditional probability for a little while. The next lesson concerns the concept of independence. So it's basically Independence Day coming up. And we'll see you then.